Standard single-pass prompts often shatter when applied to multi-file engineering tasks. Linear execution models lack the structural logic required to sustain a long-horizon project. Claude Opus 4.8 targets this limitation. It is designed to function as an orchestration engine, managing complex workflows rather than simply generating isolated blocks of text. This specific model designation, Claude Opus 4.8, represents a focus on technical reliability and systemic judgment. In multi-step code generation, errors often compound without detection. If a model misinterprets a dependency in step 1, that flaw propagates through the entire project, resulting in silent failures that are difficult to debug in production. Using Opus 4.8 as a reliable collaborator involves mastering its internal cognitive routing and deploying it across a dedicated, scalable backend. We will analyze how this model handles a code-based refactor, how it utilizes self-verification to prevent errors, and the specific virtual private server architecture required to support it. AI has transitioned from an external tool into an integrated component of the technical infrastructure stack. Consider an engineering team tasked with migrating a legacy API to a modern V2 architecture. This requires mapping thousands of lines of code across multiple files. Instead of processing this migration as a single prompt, Opus 4.8 utilizes dynamic workflows. It employs parallel execution, delegating tasks like dependency scanning and deprecation identification to independent subagents. These agents search the repository independently. Their findings are then synthesized in a central verification node, which filters out conflicting data points to build a unified logic for the migration. When the evidence is insufficient, the model triggers an uncertainty flag. This is a built-in awareness of its own limitations. The model is penalized for providing a confident answer that lacks supporting evidence. If a subagent identifies a weak assumption, it pauses the workflow. Rather than making a destructive change to the API, it requests clarification or human intervention. This self-verification layer reduces the risk of code-based corruption. In long-horizon tasks, the accuracy of the architectural map is more valuable than the speed of the code generation. Once the rules are established, the model executes the migration across the entire repository. It utilizes its context window to track hidden dependencies that are often missing from standard documentation. When a cascading build error occurs, the model does not just patch the immediate failure. It traces the stack error backward through the directory to identify the root flaw in a hidden file. By cross-referencing the error against the architectural map, the model isolates a repeated logic structure. It bypasses the surface-level syntax error to refactor the core logic universally across all affected files. This depth of analysis is managed by effort control. Setting this parameter to maximum forces the model to allocate more compute time to reasoning, which extends its search radius before it attempts a fix. This process represents architectural reasoning. It is distinct from the simple syntax corrections seen in basic AI coding assistants. Executing code without this type of judgment creates technical debt. Configuring effort controls ensures the model applies the necessary caution when modifying core services. The viability of these orchestration loops depends on the efficiency of the backend API layer. In long-running workflows, updating instructions traditionally requires a full context restart, which increases latency and cost. Mid-conversation system messages allow new permissions or constraints to be injected directly into an active data stream. This keeps the task loop running without requiring a restart. We can see the cost efficiency here. The prompt cache minimum has been reduced to 1,024 tokens. When the model accesses recurring code-based data, the cache hit indicator confirms that redundant data is not being rebuilt. Caching the repository context reduces the total latency and the cost of maintaining multi-agent loops over several hours. Developers can also utilize fast mode via the API to prioritize throughput for interactive tools, where response time is more critical than deep reasoning. These API optimizations provide the technical framework necessary to move complex, multi-agent workflows into sustainable production environments. Opus 4.8 is a proprietary cloud model accessed through an API. It is not an open-weight file that can be hosted locally. To build a secure application around this model, you need a dedicated environment. This starts with a virtual private server, or VPS, which serves as the physical host for your application. The first step is provisioning a VPS to host the application backend and API gateways. This layer manages the logic, security, and the connection to the Anthropic API. Next, a vector database is deployed on the VPS. This allows the system to use retrieval-augmented generation, feeding your private documentation into the model so it can reason with specific company context. Worker queues and cron jobs on the VPS manage the asynchronous calls. This ensures that long-running agentic tasks can continue processing in the background without timing out. High-traffic systems often use a hybrid approach. A secondary VPS running local, open-source models can handle basic data sanitization and routine tasks, only escalating complex reasoning prompts to the Opus API to save on costs. A frontier reasoning model relies on a robust infrastructure stack to handle persistent data and maintain uptime during complex, multi-stage operations. Software logic and physical hosting layers function as a single, unified system. Reliable digital collaboration occurs when verifiable reasoning is supported by stable, professional infrastructure. Opus 4.8 provides the cognitive capacity for dynamic workflows and self-verification. It allows for precise control over reasoning effort and task orchestration. This intelligence is supported by the VPS architecture, RAG databases, and API management layers that enable it to work within an enterprise environment. AI now functions as a foundational component of the modern engineering stack. Success in the next generation of software development will be defined by the ability to orchestrate these frontier models while maintaining the VPS infrastructure that powers them.